Hi everybody, this is Dr. Dadu presenting this time Higher Secondary School Certificate Pure Maths 1. Happy listening. Now, here I intend to exhibit exploits from HSC days, lower 6 upper 6. Any book on pure maths at advanced level will assist you with this series. With this particular video. I intend to discuss difference method, power series, and application. Now, starting with difference method. Difference method that I intend to highlight are of this easier type. There are functional type this or this. Now, if it is the functional type, the one I call type 1, functional type this, yes, you are looking for a function f of n that will be raised to a power, say n raised to power half, that will assist you to deal with this series. This series is the type you meet in time series, where you have u raised to power u sub n or u sub n minus 1. You also meet it in discrete modeling. So if you have a series like that, you'll be looking for a function f of n that you can write in this way that will assist you. Now, if it's of the first type, then you are going to write it out, list it out like this to serve as the representation for the un. Un will be f of n minus f of n minus 1 down the line to u1, which will be f of 1 minus f of 0. Very often, the content of the left-hand side will cancel out. Look at it. F of n minus 1 will cancel f of n minus 1. F of n minus 2 will cancel f of n minus 2. They will eliminate each other, leaving, for instance, f of n and f of 0. At most times, f of 0 will be 0. And meanwhile, this will be summing from u1 to un. So this is what will result. Most times this will be 0. Okay. So, and by the time you come this far, you will have gotten your sum of the series. Okay. If it's of the second type, look at it. It's a sequence. n plus 1, like that, n plus 2. Now, what you do is to go to the end of it and add the next one. Multiply it by the next one. Then divide by the number of terms you have multiplied. Look at what I'm saying here. This is the R term or the N term. It's a sequence. R plus 1, R plus 2, R, like that. It stops at R plus K. So what you do is to go to N plus K plus 1. We use it to multiply the numerator. Then you will have had as much as K plus 2 times. Mind it, you're starting from ordinary N. So you'll have come as far as K plus 2 times. So we are dividing by K plus 2. This expression is the sum of this series. Okay. Example. If we want to sum this, for instance, it is of the first type. So our f of n will be f of n equals n raised to power 5. All right. So as you write it out, f of n minus f of n minus 1 down to 0 like that, you will notice that everything gets eliminated, like I said, leaving you with n raised to power 5 on the left-hand side. Meanwhile, the sum on the right-hand side, if you sum it layer by layer like that, first part, this will result. Second term, this will result. Third term, that will result, like that. So this is the sum that will result. But mind it, what we are looking for is sum of r raised to power 4. And that is in this expression. So we'll have to make it the subject. As you make it the subject, this results. Meanwhile, these ones, there are identities for them. Sum of r cubed, it has an identity. Sum of r squared, sum of r, sum of 1. Sum of r cubed is n times n plus 1 over 2 all squared. Sum of r squared is n times n plus 1 times 2n plus 1 over 6. So sum of r is equal to n times n plus 1 over 2. And sum of 1 is n. So those ones if you put them in their respective offices, this will result. All you need to do is to simplify further and use these 5 to divide throughout so that you have an expression that looks like it. And you can check whether it works. Iterate it for r equals 1, r equals 2, and see whether it will be equal to the right-hand side. Now, of the second type, like I said, look at 1, 2, 3 increment of 1. So the n term or the r term will be this. So all you do is to go to the next one, which will be n plus 3. Use it to multiply this. So how many times would that now be 4? 1, 2, 3. So you divide by 4, and this will result. So the sum of the term is this. Sum of the terms of this series is this, easily. But many a time, this will not go follow a sequential order, just like in this example. It doesn't follow a sequential order here. So if it doesn't follow a sequential order, you get the n term, you expand the n term, write it in terms of r, and put the sum with it. So you will now use the identities. Okay, the identities are here. Yes, you see. R cubed is this, R squared is that, R n is that. Put them in their respective offices and simplify you to the last, and this will result. The next is power series and the applications. Series of this nature are known as power series. Now, a popular example is when you do the expansion of 1 plus x raised to power n, a binomial expansion that is. And you know, as this results, you can find the sum. The sum will be this. Luckily, the first term is 1. So the sum of n terms will be this. Okay. Now, if you differentiate, if for instance we are asked to produce the sum for this series, then we will think about the series that looks like this. This is a series that is very easily to sum. The first term is x. The common ratio is also x. As such, if we use Sn to be a, 1 minus Rn divided by 1 minus R, the sum will be this. So the sum of this series is easily this. And mind it, this is what is required, but by differentiating this, what will result? This is what will result. So the series we want to sum is what will result. So we merely just differentiate it, differentiate both sides here to get the sum of this series. And that's what is done here. But as this series is, it gives us avenues to get the sum of n terms of series that looks like it. An example is this. How does it look like it? You see that 2 is sitting in the office of x. If you write 2 in the office of x here, this will result. So just go to the sum of n terms and put 2 in the office of x, and that's it. Again, here 3 is sitting in the office of x. Just put it in there. Here, -1 is sitting in the office of x. Put it there, and you get the sum easily. There's a special power series. This is the series. It's an oscillatory series. Just positive, negative, positive, oscillatory. But what is interesting about this series is that this is its n term. N is squared. If n is squared, then the corresponding sum will have been n plus 1 times 2n plus 1 over 6. But this does not work for the sum of the series. That's why it's a special series anyway. This is the series that works for it. And to show that it works for it, I did the mathematical induction proof to show that that's the sum that works for it. I don't know of any other. Maybe you can think of some other. This is the farthest I intend to go here. Watch out for the next in this series. Please like, share, and subscribe. Thanks for listening. See you next time. Thank you.